Hi, good afternoon, and thank you so much for having me in St. Petersburg. To the conference organizers, the city is incredible, and I'm so enjoying my time here. I'm enjoying learning from everybody. A special thanks to another speaker, Nissan Hermanti, who loaned me his laptop so that way that I can confidently speak. I had some technical issues traveling from the States. So thanks to him, and you should check out his talk tomorrow. So today I am going to be talking about property testing and in the hypothesis library with Python. And I'm going to be talking about it from the perspective of making our test suites more robust. So who am I? I am Jessica Ingrassellino. I have my doctorate in education, and I'm currently the director of quality engineering at salesforce.org for the education and the nonprofit clouds. I am also the founder of teachcode.org, and through my company, I teach adults who are re-entering the workforce, as well as students and children of all ages, how to code in Python and about testing and security. So today's talk is an introductory talk. So you saw the little smoothie on the program, and this is an intro talk to property testing. What is it? Why would you use it? And then how can you use the Python hypothesis library in order to create property tests with structured random data? So property testing isn't new. That's the first thing. But I do think that there's a lot more discussion about the possibilities of property testing. So as a test engineer, before I became the quality director, I learned about property testing while I was doing research about the different ways of making testing more efficient and more robust. I've gone through the unit tests at salesforce.org, and I've talked with engineers at other companies that I've worked for about the unit tests. How can we make them more robust? How can we add the information that we need without putting more pressure on developers, and in ways that we can incorporate all of the members of our development community? So incorporating information from our testers, our developers, our project managers, and making sure that we're really thinking of our whole product holistically and getting to test in holistic, systemic ways. So some of the things that I got to thinking about were some of the UI frameworks that I've used in testing. So, I thought, well, Cucumber uses example tables to define multiple scenarios for UI testing, so it doesn't seem so strange to have property testing actually also do something similar. So today's example code, we're going to be working with the Caesar shift. It's a pretty simple shift function, pretty simple cipher, and we're going to walk through this and each of the elements of this and how we can replace some of the example-based tests with some property-based tests. So how many people in the room have done property testing with quick check or hypothesis before? Or any unit test? Okay, and for how many people is this kind of totally new? Okay, good, you're in the right place. This is good. So this is a great way, a simple piece of code is a great way to get to learn the hypothesis library. And I highly recommend starting with something so that way that you can sort of rip up the code. So this Caesar cipher essentially works, if you haven't seen it before, it just works by shifting the alphabet from one to another position, a given number of letters depending upon the shift. And you can also shift backward if you use a negative number instead of a positive number in the shift. And in the sample that we're using today, we're going to be working with ASCII characters 97 through 122, which are the lowercase English alphabet characters. So when I reference either the alphabet or ASCII characters, That's what I'm referring to. So here's an example-based test. And example-based test, for those of you who haven't used that language before, is just another word for unit test. It's very similar to our standard unit test. So in this case, we have 3 as the distance of the shift. We have our letter to be encoded, and we have our expected result of the encoding. So we want to start with the letter A. We expect the lowercase letter d to come out. And there are some things that I have questions about. What about other inputs and letters? What about other shift lengths? What happens if I enter a non-ASCII character from that range, or a character that's out of range? What happens if I enter a string into the shift length, or a number into where I'm supposed to put the string? What if I miss something? So some of the limitations of using example-based testing are that we don't always know what we don't know. And so, for example, we might say, oh, well, this is really easy because I just want to test 1 through 26. Because there's 26 ASCII characters. Okay, well, what about looping over? What happens when you get to the end? What about your boundary conditions? What happens when you do the incorrect type? We don't know what the code even works for. And we would need multiple tests, multiple standard example-based unit tests to cover each of these unknowns. And every single one of the unit tests comes with a level of cost and maintenance in order to keep it working and functioning properly, and comes with cost and maintenance if there is a change to the behavior. So the question then becomes, how do we overcome these limitations? So David Mclver, who is the author of the Hypothesis Library, tells us that property testing is an extension of our normal testing tools. It looks similar to an example-based test, and it really does. Instead, you are telling the test library how to set up the data you want, and there are times when you can just replace your example-based test with a property-based test. So property-based tests can be faster and more efficient, and they use structured random data to the developer's specification. So you can create an instance where your data is controlled and repeatable. It's not this completely random thing, or at least it doesn't have to be. So today we're going to look at just how we can get these so-called better results. How can we address these edge cases that we might not find? How can we find those errors that we might not think about when we're deep in the thick of writing our code and trying to get the unit tests out and get that code deployed? How can we deal with legacy code? Code bases that are under-tested, that were just deployed very quickly because something needed to get out the door, which is a business case that happens. And it might not be best practice, but it's a thing that happens in reality. How do we address those legacy code bases when it suddenly becomes our responsibility? Property-based testing can let us explore some of those systems with structured data. So we'll talk about some ways to do that. And overall, we can increase the robustness and the coverage of our code. And I think this is great, but I'm not the only one saying it. So John Hughes, who is one of the developers of QuickCheck and now has his own company that does this kind of testing, used property-based testing to go through 3,000 pages of specs for, there were 6 different suppliers of third-party code for Volvo. And his team wrote 20,000 lines of QuickCheck. They went through 1 million lines of legacy-based code, and they found 200 bugs, and 100 of those bugs were in what was considered the standard code. So in the end, they had smaller test code. They found bugs in a legacy system. And this is in a legacy system at scale in an industry. So I just do want to point out for those of you who might be new to this or have heard that property testing is crazy, doesn't have to be, and it is already in use. It's also not this brand new idea. But the myths persist. So a lot of people who are anti-PBT, no, there's no control over the test inputs. Untrue. There can be no control. You can do it that way. It is just not recommended. The inputs can be specified in a variety of ways. And we'll talk about some of the ways that you can use hypothesis in order to create these inputs. There are many libraries for property-based testing in many languages. So you can go ahead and take a look if it's in your language. I think hypothesis is currently being implemented in Ruby and Java right now. So there are multiple implementations of different property-based testing frameworks to make this easy. The next argument, the tests are flaky because the input's always changing. Okay? This can be mitigated with several of the features that allow you to actually define the data that you want to have going into your tests. And another thing that's really helpful is that hypothesis has built-in shrinking strategies that actually break down the failing data and report it back so that way you can test and retest it. Then random data and testing is a testing anti-pattern. Sure is, but this isn't random data. It's only an anti-pattern if you're just throwing crap at your code. But if you are thinking with a process about what you are doing, then you can actually add a lot of value to your tests by using the data generation tools in a library like Hypothesis. So now that we're addressing some of these questions and concerns, some of our myths of property testing, we're going to start to take a look at this Hypothesis library. So I love this library. I have to tell you, this library has just made testing interesting and really fun for me to learn about. It allows you to use structured random data for testing through a series of strategies. It's pretty fast, so you can have 500 data samples tested in 3.1 seconds. If you had to write 500 example-based unit tests or 500 asserts, you wouldn't have that same kind of speed. So it gives you a little bit of a speed uptick too. This library specifically is used by the Hypothesis project, Mercurial, PyPy, Apache, Arrow, edX, Pandas, and other projects. And there are some resources in the end of my slides, which I'll share on the website, where you can access some of the open source libraries that are actually using this and take a look at the code base, because it's really fascinating to see how people are building out the strategies. So again, this is really good for those errors that are easy to ignore or easy to forget about because you're going so fast. So taking a look at the parts of our property test, we have, again, it's similar to our example-based test, but we have a section for us to actually write our test cases out, much in the way that we do in our standard library. Then we have a section for generators, special functions used to generate our data, and we have a place to highlight those in the test. And then we can add helper functions, which help us to do some of the setup work that we require. And running our test, we have the availability of shrinking methods to capture our failures. We can log our failures in a database that is dynamic. And then we can automatically rerun our failing examples until they're fixed. So hypothesis tests look a little bit different, but not so much different than our example-based tests. You'll notice that I have the given and the settings decorators, and I'll talk about what each of those things can do. The strategies specified are generating random characters. So you'll notice that I have the S variable instead of actually putting in the characters that are being encoded. And now, instead of testing from A to D, like I did in the example test, I can test a shift of 1 on any character I choose in the alphabet. Now, there is some missing code here. So the variables that I had at the top that defined what the exact letters were and how I was getting those out of the ASCII library, those are missing. So this isn't the full example code. So just do keep that in mind, that I tried to maximize it just for visibility on the slides. So now, instead of the single character, we can test everything. We can test our boundary values. We can test characters in the middle. We can make sure that we have every instance of one shift covered. So how are we doing this? The nitty-gritty. Lady, tell us the strategies. All right. So we're back to our code, and we basically, you'll notice that there is some error handling in this code. And this isn't the test code, this is the actual functional code. So we have our raising the exception in case somebody enters a shift that's if they want 4 instead of the letter A, can't have it, sorry, here's an error message instead. If there's an empty string, you can have that. And then the shift code is handled on the bottom. So that's the actual, quote, production code in this instance. So in order to reduce the complexity, we're going to take a look at some of the basic tests that I came up with when I first built this. And this is from like a while ago. And as I was building out the tests, there were basically 8 tests that I started with. Had my empty string tests, have my boundary tests, just at the 0, at the 1 shift. I didn't even think to put a negative shift in there. I didn't even do that. I did do a loop. And I have the 2 negative tests for my error messages. Now, what do all of these tests have in common? Each one tests a single example. So 8 tests, 8 things tested. Seems legit, especially when you have to write all of them out, right? But what are the properties of these tests? What is it that we're actually trying to get at? So first of all, when we're designing and thinking about property testing, it isn't just about this cool library, although mostly for me it's about the cool library, but it isn't just about the cool library. It's about thinking of what is it that I always expect my code to do, no matter what. What are the properties of this code? It could be a function, it could be a class, it could be a program, it could be an entire system. What do I want it to do? Well, the properties of this code, any given lowercase English letter from position 97 to position 122 should yield a successful shift. That's a property. No matter what I throw, if I throw A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, they should all shift. Any given shift length, I should be able to put a shift length of 1, of -1, of 9,762. It should always loop, no matter what I do. So any whole number should work, any integer. If there's an incorrect data type, it should throw an error of some kind. And my empty string should return empty because I wrote the error code for that, so that's the behavior I expect. So I'm going from those 8 examples that I gave you, and now I'm moving to 5 test ideas. And these tests are designed to capture the properties. So there are a lot of other behaviors that we could think about. And for each, we could create a property-based test and then we can use the hypothesis library to create the random data for that test, and we can actually get a lot more with a lot less tests. So before, I had my 8 tests, my 8 example-based tests, and I could get 8 results. Now, any letter, 26 potential letters in the combination that I have, with any shift, say I have 26 shifts, I could test more if I felt really ambitious. That's 676 cases right there, 5 test methods, right? My encode cases give me another 3 cases minimum. My empty string and my shift with a float, 2 cases. So I've got a minimum of 682 different cases covered, different test cases with 5 test methods. So this is something, like I mentioned, fun to play around with simple code and really practicing thinking in properties instead of thinking in examples, because we're really good at thinking in examples, because it's how we've all been trained to think about writing tests. So getting in and thinking about properties makes the proposition a lot more interesting, in my opinion, and to me, it's made it a lot more fun. So we're going to talk about 2 strategies today. And I'm going to break them down so that way you can see how you can read through the hypothesis documents and hopefully figure out how to use any of the strategies that you choose. So I will start today with the text-based strategy. So the hypothesis strategy.text, in the given area, you'll notice that I've put strategy.text. And then I have my variables, which are accepting whatever data strategy.text decides to create. So I don't have any parameters defined. You'll notice that the strategy.text function has nothing in those parentheses. That means that the data is completely random. So what's cool is that you can use it right out of the box. Import hypothesis, at given, import at given, strategy.text, and then, write your test, run it, and then this happens. I'm trying to test a Caesar shift. Not helpful. It's cool. It's cool that it generated all of that. This is a sample of 12, I think, out of the 200, but it just literally generates random data. So we need to add the parameters in order to get the data that we actually require for our tests. So each of the individual strategies in hypothesis has a number of parameters that the developer can actually implement in order to narrow down the focus of the data. You can also, there are also ways where you can assign custom variables, so custom list, custom dictionaries, custom strings to be in your alphabet as well. So it doesn't have to be a Python string method. It can be, but it doesn't need to be. So in this instance, the ASCII lowercase method gives me exactly the range that I wanted. So I was like, sweet, amazing, great. And I'm only in this method able to test the shift of 1. So I don't need to go nuts with lowercase strings of 36 letters because they'll fail, I know this. And that's not useful. So the other thing to note is that these parameters are not required at all. You can leave them completely blank as we did, but be warned, it will be very random. So adding the customization goes right into the given decorator when you actually add that to your test. And then you'll notice that I've, again, highlighted all of my main functions. And now let's take a look at the data that's actually generated from specifying. And this is data that I just pulled randomly, literally copied and pasted it from my results. And so I've got lots of samples of single letters that are lowercase ASCII characters. So using a random data library, I've structured that data so it's doing what I need it to do and giving me what I need for my tests. Now, Hypothesis will take your data and it will run your tests until all of the possibilities have been exhausted, and it will keep running them to give you the amount. So it will take the ASCII string, which is 26 lowercase letters, and it'll just keep throwing them in whatever order, and it will run all of them if I do 200, and it will make sure that all of them have been exhausted. If there's a failure, the test stops, and then it gives you a way to actually rerun the failure, and I'll go over that in more detail. So essentially, when I did this test, it's a very simple test, but I ran one test to do that shift, 200 assertions, and less than 1/10 of a second. So I'm good, I'm happy about this. So let's see another strategy, because letters is, that's really nice, but it's not the only thing that exists. So another basic thing, integers. So if you recall, we had our basic tests, and we had our shift of 1. So now what we need to make sure of, our property, is that we can put any positive or negative integer into that space and have a resulting correct shift. That's the property that we want to test. So reminders of our rules, specifically any number of spaces, loops after reaching the beginning or the end, and any integer, positive or negative, results in a shift. So with our integer strategy, really the two things that you define are the minimum or maximum size of the integer. And when I did this, I just went with -90 and +156 because I felt like it. I wanted to see what would happen. If you wanted a really tight sample, you could go in closer ranges. If you are exploring, let's say that you're in an application and you're not sure what's going to happen, you kind of want to see what would happen if. This is a good place to say, maybe let me try -10,540 and +4. So in this way, you can start to sort of explore your application, even if you're not entirely sure what the outcome might be. I went with this randomly. You can tighten it up to be very specific. So using the integer strategy, I defined it in the same exact way as I defined the text strategy. I have both of the integers there, and then I've got my x variable, and I'm testing them all on encoding the letter A, because why not? So here's the values that resulted, and you can do verbose reporting. So if you have the output set to verbose, then you can get all this information. So you also know exactly what hit your test. You know what passed as well as what failed. And you can notice that there are negative values, there are positive values, but all of these passed. So we've got tests that were within 1, 2, 5. We have tests that went negative and looped backward, all the negative tests, all the positive tests that looped over. So all of those passed, which is great. That's awesome for us. So I'm about to show you the worst practice. I know, why, right? But, why? But it was an experiment. I wanted to see if I could do it. And this is a loosely held opinion, and I'm perfectly willing to change it because this was mostly based on me kind of tearing this apart and seeing what I could do with a library. So I decided to test with multiple strategies. So I was like, what would happen if I threw random letters and random numbers at the shift and tested them at the same time? But we know, not a great idea to test two things in one unit, like bad, boo. It's not what you do. But I kind of couldn't really help myself there. So I did it, but I'm not recommending that you do it. And now I just can't access my video. Oh, there we are. Okay, so in this example, we have the two variables. Like I said, two variables are changing. You can see in the test where I defined an integer strategy and a text strategy, and you can do that. Even if you're doing best practice testing, you can do that. And then I ran my samples, and I got the output, defined what was tested, and then you can see, you can go through with this tool, you can look at every single outcome and make sure, hey, it actually did the things that I expected it was going to do. And another thing that I asked it to do in the second run after I videoed this was I added a print statement so I could see what the resulting shift was, so I could make sure that it actually did what I wanted. Again, I get it, not best practice, but I was curious. And it does actually get at some more important things that are best practice later. So here's that code again, just a little bit more clear. And here's the output of that code once I added the print statement. So you can see there, again, our negative and positive integers, our single, and our resulting things. Now, why on earth would you do this? Well, if you have an area, and this goes into kind of the legacy code thinking. If you have a legacy code base, if you have a function and you have no idea what it does, or if you're not totally sure, you can you can think, okay, well, what is the property? Write a strategy and start to throw some data at it and learn what it's doing by observing it. So it's an interesting way and a different way to observe behavior. So the library for the strategies is pretty substantial, and every single one of these strategies has a way to customize it. So you can do some date time testing, you can do things with lists and dictionaries, and you can really get very detailed building out strategies. So speaking of building out strategies, custom strategies are a great way to actually test your code when the standard strategies just won't get you where you need to be. So to build a custom strategy, you can chain multiple strategies using strategy.builds, and I'll show you some examples of that. You can use filtering, mapping, and chaining, which are all built-in parts of the hypothesis library. You can use draw to combine strategies as needed as the tests are running, and all of that intelligence is built into hypothesis. So this example is an example of an object for testing movies. So using strategy.builds, I have my movie object, and then I've assigned the strategy.text undefined, so we know it's going to come out badly, but you could define ASCII characters or string.ascii underscore lowercase and assign actually valuable data to those text strategies, and then the price strategy to communicate the min and max value of the movie in American dollars in the format of an American dollar, although that could also be changed to any preference. So that's one way you can build a custom strategy. Another custom strategy, and this comes from Alex Chan, is using those integer strategies to chain and build out an RGB color tester. So if you need to use this in any way, shape, or form, you can simply chain the strategies, and then you can use that color strategy in the given call, and it will generate 200, 300, 500 RGB combo, however many you felt like. And then finally, this is a DNS label test, and this comes from Glyph and the Twisted project, and that's on GitHub, so you can check it out. They have a whole library of custom objects and custom builds and custom tests that they've done with Hypothesis, and they're using the text and defining it very, very specifically with what they want in that string, and then the minimum and the maximum size of the string, and then filtering it out so that way that the data comes in the exact format that they need. And they are using this to do DNS testing. So you actually can go and look at that code. It's pretty awesome. When I looked at it, I was really impressed. It's a little much to go into in this talk, but well worth exploring. So now comes the thing. How do we avoid flaky tests since we're throwing all this randomness? Because flaky tests are awful. It's a concern with using random data to have flaky tests, and it's also really bad when you have to be the person to go figure out why something is flaky. It's very frustrating, or at least I find it very frustrating. So Hypothesis gives us shrinking. We can find the simplest example of our failure. So what happens is when Hypothesis finds a failing example, it then immediately starts with that example finding and running other things that are similar, but it starts shrinking them down smaller and smaller and smaller until it finds you the smallest failing example that it can. So for each strategy also comes with its own example. So for example, the string shrinks by decreasing the size of the string with every failure based on the original failing string. List failure works by first removing elements from the list until it isolates the element that's failing, and then removing parts of the actual failing element that's in the list. And every one of those strategies that I had up a few slides ago has its own methodology of shrinking your examples so that way that it can really isolate the failure for you. And then, what happens with those examples? Well, first of all, they are reported out to you when you run your code. They're actually reported out in a tag that you can run, and I'll show you that in the next slide. But those examples are all stored in a database that is created automatically every time you run Hypothesis. And these examples not only store your failures, but also if there's code that's run and there's examples that tend to touch that code, it will store that too. So the database that stores these examples is checked into, it can be checked into version control if you choose. So that way that if you're working with multiple people, it's always up to date on what's failing versus what's not failing. It's also updated on the fly. So if you have an example that fails and you adjust your test so that way that no longer fails, then that sample is removed from the failures database. Hypothesis also runs the failures database every single time you run your tests. So it helps you to keep track of exactly the failures. Now, the only thing to keep in mind is that the known failing examples, if you really have an example that you must run, you should define that, and there is a way to define that, so that way that you always have what you need available. So that is called the example decorator. And the example allows you to specify what it is that must be run every single time, no matter what. So this allows your structured random data to also include example data. It's kind of the best of both worlds. You get your example-based test, but then you can also have some of the structured random data built in. Each example gets its own tag. So if I wanted another S and another X definition, I would need to do another example tag. So that was something I discovered after a lot of frustration. It's not in the docs. So the other thing that you will get in a readout is this reproduce failure decorator. So when you fail and it has the smallest example that it made, then you have your failure decorator, and you can use it by just pasting it in underneath either the given tag or the example tag. And if you want it to always print out your example decorator, you can put your settings so that way that you're always getting all the information out of your tests. So now we kind of know the basics of how to dig into the documentation, of how to start working with all of the different strategies that are available. We need to think about what are the patterns of the properties that would be in our code. And most of these are things that you're probably aware of and that we don't simultaneously think about because, at least for me, I know the pressure on me comes in the form of, what can it ship? Can we ship it? You know, so this helps us to think ahead about strategies. So the first property that we're going to think about is different paths, same destination. So when you're looking at code, whether it's new code that you're planning to build, or whether it's legacy code, or whether it's code that you just want to update the test on, when multiple things can happen on a data set, and those are unordered operations, is the output always the same? That's a general property of code, being commutative. So, or that can be a general property of code. If that's a property of your code, then you can use strategies to generate data that should be able to be handled by that code, and if it's not, then you've found something that you can test. So this is pretty useful in list sorting, in list reversal, and in other strategies. And then the property of symmetry. So anywhere that you want to ensure that your code isn't losing information when it goes through multiple operations, so like parsing text, encode decode, serialization, you can actually use this. Some people call it round tripping, some people call it symmetry. It's referred to in different ways, but you want to make sure, if you want to make sure that your data is actually going through and comes out the same way it went in, then you can throw a lot of data using a strategy. You can throw different kinds of data using a strategy and figure out if there's anything sort of funny. Now, this was used in production by the Cassandra project at Apache. They used this kind of testing, specifically symmetry testing with a property-based framework. And with the round-trip approach, they found and fixed a bug in a feature for data integrity. So that was found, fixed, based on property testing thinking of this property in mind. So these are things that people are really actually doing. So hard to prove, easy to verify is a pattern where rewriting the implementation for your test is basically like writing the production code and putting it into your test. So that's not really a best practice, right? We don't want our tests to just be our production code because we're not really testing it then, are we? So what we want to do is figure out what property of the code could be implied from a potential answer. And then we can create tests and generate data to verify the property or an end result, and then we're able to, again, throw lots of our samples in our structured random data and test that out. So this might be applied in testing a string tokenizer, prime number factorization, or other problems or algorithms of that nature. So then invariants are basically the key logical rules that should be obeyed throughout your program. And they're better understood by humans than computers, probably. And they might not always be obeyed within the program, meaning you start with something, some business happens in the middle, you end with something. And the beginning and the end are expected. But the invariants might not be totally, your compiler might not understand them even if you do. So how do we manage sort of the big picture statements in complicated software? Something that we can do is ensure that we are actually checking that our information is completely preserved no matter what's happening in the middle. And some examples of where you might use this, this property or look for this property are places where you want to check where strings or list sizes after mapping have been preserved, or any kind of list contents or sorting. So model-based testing, oracles, it's thinking about this property is thinking very, very high level about what it is that you actually believe that your software is supposed to be doing. And you can use a previous or a different model for the same behavior. So for example, if you are at a company and you have a single-threaded algorithm that's processing data, and now you want a multi-threaded algorithm, but it's still, both should process the data the same way. But hopefully the multi-threaded one does it faster. But the outcome should be the same. So in order to test those outcomes, you could use the old model to inform your testing and your expected outcomes. That's a potential. Models are all around us. If you are creating something brand new, greenfield, then you can make a very simple, high-level model and talk about the properties of that model. And it might be clumsy, but it should be obvious what it's trying to do. And then use that model to test against with your property-based testing. So you can also adjust your model as you adjust your system, and you can use that to derive new properties for the testing. So all of these are different ways to engage in testing with hypothesis. Now, this one is definitely controversial, and I ran into it, but then I put it up because I thought, you know what? Some people like to experiment, and so do I. So if you want to do hypothesis in TDD, instead of writing the one test, like for the Caesar shift, instead of writing a shift of A with 3 will equal D, I could have made a strategy and just thrown a bunch of stuff at it and figured out like what was going to happen. If you feel so bold as to experiment this way, design with your properties in mind rather than your examples, write your strategy, your test, your strategy, and your data first, then go ahead and write your code, and then run your test against the code that you've written. It's going to be really different because you're going to get random specific data thrown at your test every time. So it has the potential to be interesting. For production, in terms of like if you have to go to work, would I do this at work? Probably not. But would I do it for fun? Yeah, I would. Because I'd love to see, I like to experiment and see what happens with things. So it can be used in TDD. People have very different opinions about whether or not one should do that, and you should go read about them. Finally, you can examine your legacy code, and again, you can take the approach of sort of like almost like fuzzing to learn. So going in, finding an unused area of the code base, using hypothesis or another library, set up your examples, design your test data for what you think you're looking for, and then try it out and see what happens. Try to build those things and use it almost as an exploratory testing technique with code. So just want to another example of property testing in legacy code in production. So John Wayne Norton at Google, his story was featured in the Foundations of Property-Based Testing book, and he ran around 600 lines of property-based testing code on Google's LevelDB, found 17 and 31 calls that could corrupt databases with ghost keys. And those errors had been there for a while. It wasn't a new database that he ran this on. The errors had been there, and they were just kind of hiding out, waiting to be found. So that technique of exploring with property-based testing is another technique. It's been done. It's been done in production. So thinking about all of the different ways that you might use this, or maybe might not use this, depending on your circumstance, and really looking to find what I consider to be like the fun aspect of this, which is maybe that nobody thinks testing is fun, but I think exploring ways to make our code stronger, ways to make it less brittle, addressing different properties of code and thinking about code in a more broad sense as opposed to in the 1+1 sense. I think and really want to emphasize structured random data as everything. It's not just random, as we saw in the beginning. We've got to structure it. And thinking in properties, it's a different way to think about unit testing. It's not about examples. It's about overarching behaviors. And think about what is it that you really want to learn about your code when you're testing. What do you want your test to tell you? If you want your test only ever to tell you that 1+1 is 2, cool, write that test. If you want your test to tell you something about how it's doing the math, then write that test. And property-based testing can help you write that test and get to learn what it is that you really want to know from your code. So thank you so much for having me. I absolutely appreciate your attention and patience, and I look forward to speaking with all of you soon. Thanks.
Thank you, Jessica. We have some time for questions. Questions?
No.
Could you describe some productions that you've used in some examples that you've used in production for testing and some of the things that you found were helpful?
So right now we haven't been able to apply it in production yet because we're kind of going through our audit of our unit tests. And the other thing is that we have, so at Salesforce we're in Apex, and so all our unit testing currently is in Apex. And I can't find an Apex library for property testing, but I've been researching. I can't believe I'm saying this out loud. I've been researching writing one because I really that's how I feel about that's how strongly I feel about the fact that complex systems should be able to have more complex tests. And right now, personal opinion, I don't think that ours are complex enough because again, they're in that example-based framework where we're just picking out like the basic, like here's the happy path and maybe here's a negative test. And it's like, why? So we're working on it.
Thank you.